Everyone. This is Will. Welcome to Hangout number 2 for the miniKanren uncourse, which is sort of an informal discussion of miniKanren programming and relational programming in miniKanren in general, and different ways to do relational programming or logic programming. Basically, anything in that area is fair game. The way we did it last time was the beginning. I was talking about a couple concepts related to miniKanren. Last time I spent most of the time talking about unification, or equal in miniKanren. Today we're going to talk about the other two core parts of miniKanren, fresh and cond. And we'll talk a little bit about, hopefully we'll talk a little bit about sort of the canonical example of relational programming, symbolic relational programming in my mind, which is append. And append is a program that looks relatively simple, but actually has a lot of depth in it. And even if you've seen append before or appendo before, there's a lot to talk about and a lot to understand. I think actually not that many people really understand everything there is to know about append. And I probably don't understand everything there is to know about append. It's a very deep program in a way. So talk about that a little bit. And then the second half of the program, we just kind of open it up. Anyone has questions, anything they want to talk about, if we want to do some hacking, whatever it is. That's sort of the super informal part. Okay. So we got some people in IRC. Before I go any further, I should probably show some things we created from last time, some resources that might be useful to people. So let me try screen sharing here. Okay, here we go. So hopefully you can see this. This is the GitHub repo for the miniKanren uncourse. And it has a few things in it. For one thing, it has the implementations of miniKanren that I'm using. So right now I just have the scheme version. This version of miniKanren has lots of support for symbolic programming. It has special constraints, one called symbolo, which is sort of like symbol question mark in scheme to see if something's a symbol, or to enforce if something's a symbol. Another one's called numbero, which is like number question mark in scheme, but enforces, it's basically a constraint that enforces a value as a number. Also has something called absento, which is saying a certain term doesn't appear inside another term. It has disequality constraints, which are sort of the dual of unification. It's kind of the saying two terms aren't the same. And those constraints are very interesting and very useful, especially when you're writing programs that manipulate other programs, things like that. I don't know that we'll get to any of those today, but we'll get to them soon. But I still consider those maybe slightly more advanced than what we're going to do today. So we want to make sure we have a really solid foundation on core miniKanren first. But anyway, this is the scheme implementation that I tend to use. It doesn't have everything in it that you might want. It doesn't have number-based constraints in it, for example. Constraint logic programming or finite domains. Doesn't have nominal logic support. If you don't know what those things are, don't worry about it. We'll get to them later. But anyway, this is what I use when I'm doing my own hacking, basically. So that's this is a version that runs in Scheme. I use Vicari Scheme. Sometimes I use Shea Scheme, but should run with maybe slight modification in pretty much any R5RS or R6RS compatible scheme system. You can also run it in Racket under the R6RS compatibility mode. And I think we can probably add some other implementations here, maybe in other languages besides Scheme at some point. Also, we have Hangouts by date. And in this subdirectory, right now we only have one date. We have the Emacs transcript from last time. So this is all the code from the live coding from last time. So if you want to check that out or run it, go ahead. And some information about the Hangout with like the link to the YouTube URL. And the YouTube video that's up actually has links to different parts of the Hangout, so if people want to skip ahead or whatever. The other thing that's useful about this uncourse GitHub repo is there's a wiki, and this also has links. And what I want to make sure we can do is keep adding pages to topics we've talked about. So here's the page from the first Hangout, and some of the things we talked about: unification, co-inductive logic programming, that sort of thing. So for the co-inductive logic programming page, just have a lot of resources related to that. So hopefully we can turn this into a site that has lots of information about different types of logic programming, relational programming resources, and so forth. And feel free to edit the wiki and add links, and add pages, whatever you want. Okay. All right. Also, we have an IRC channel. It's the miniKanren room in the Freenode IRC. Let's see, what's the link to that? I've got the link in various places, but let me just make sure I get it for real. I guess I have it on the uncourse page, actually. So yes, irc.freenode.net, and miniKanren is the room. Okay, so I'll be looking at that and the chats in the Google Hangout also. All right, so those are resources. Feel free to experiment and add to those, please. Without further ado, let's go ahead and talk miniKanren. I guess before we begin, are there any questions from last time from talking about unification or anything like that?
Not for me.
Okay. Alrighty. Here we go. So I'll bring up my Emacs. Okay. All right. So miniKanren. So last Hangout, we spent a lot of time looking at the equal operator in miniKanren, which is basically a form of equality. It's an equality constraint. Think of it that way. So we can say 5 and 5 are the same, for example. And we use this run operator, which is basically the interface between miniKanren and Scheme. And we talked about how you could try to say things like, okay, well, we want to enforce that 5 and 6 are the same, and miniKanren will respond with the empty list saying, well, basically there are no solutions. There are no values of our query variable q for which 5 and 6 are the same. And whereas in the first run expression, if we asked what is the value of our query variable q for which 5 is equal to 5, we get back this _0 in the list, which means that q can be anything. That's miniKanren's way of representing any value. So q could have any value whatsoever, and 5 would be equal to 5. Right. So last time we talked about this notion of equality or equality constraints using equal. We talked about the run interface. We talked about the query variable that we're using, and we talked about the answers. And of course, we use this run one to say we want one answer back if it exists. If if we want 2 answers, we can do a run 2. Now, when we're trying to say that 5 and 6 should be the same, there are no answers. There are no values of q that will make 5 and 6 the same, so we get back the empty list representing no answer at all. If we want 5 and 5 to be the same, of course, there's only one answer, because we have this most general answer. Q could be, the query variable q could have any value. Okay, so miniKanren can represent all the infinite possible values of q as a single _0. So run 1, run 2, run star. In this case, with just a single call to equal, they're basically the same thing. You can't tell any difference. Okay? We're going to change that by adding another operator to the language called cond, which is going to allow us to have multiple answers from a run. And being able to get multiple answers back is one thing that distinguishes logic programming or relational programming from other styles of programming. Okay. Now I should stop and just go ahead and say that miniKanren, or the version of miniKanren I'm using, is embedded in Scheme. So when I say that we're going to get back multiple answers, and that's something special about logic programming or relational programming as opposed to other styles of programming like functional programming, you have to wait and say, wait, if this is embedded in Scheme, which is a functional language, then how are you able to get multiple answers back if that's not part of functional programming? And of course, we're basically simulating these multiple answers, right? We're getting back really one answer, which is a list, but we're lazily generating this list of answers, so we're only getting back the answers we asked for. And we could get back a lazy list of infinitely many answers when we ask for the first 5, let's say, that kind of thing. So Scheme is, in some sense, just giving us one answer, but that answer is a potentially infinite list, and we can ask for as much of that list as we want. And we're treating those different values in that list as different answers. Okay, so if you're familiar with things like streams or lazy streams, infinite streams, lazy lists, that's basically what's going on under the hood. But we're thinking of it in the terms of getting multiple answers back. Okay, multiple answers that satisfy our constraints. So let's go ahead and get back a program, and you'll get back a couple answers here. So let's first of all modify our query a little bit. So here we're asking, is there a value of our query variable q that would make q and 5 the same, make them equal? And of course there is an answer. The answer is q is 5. And we see that in the list of answers we get back, list 5. All right? Now to get back more than one answer, we're going to use a construct called cond. And cond's syntax is borrowed from Scheme's cond operator, which I'm probably not going to get into because it's not really important. If you don't know Scheme, don't care about Scheme or whatever, so it doesn't really matter. But the idea of cond in Scheme is that it basically is like an if. It's like an if. You can have as many branches as you want, though, as many tests as you want. And we're copying that syntax from Scheme. Okay, so if that's where the name cond came from. The E part stands for every, as in you can get every answer. So the way it works with cond is cond can have one or more clauses, and each clause can have one or more what are called goals in miniKanren. Okay, so we say equal is a goal. Technically, that's not right. It's a goal constructor, but right now we're going to kind of blur the terminology. So basically, it means in each clause I can put equals. I can put other conds that are nested. Any of the other parts of miniKanren that I'm going to show you, any of the other constraints, any of the other operators, you can put inside a clause. Okay, and then there's a set of parens outside the clause to show the beginning and the end of it. But I could have more than one equal if I want to in a clause. We'll talk about what that means also, but that's just the syntax of it. Okay, so you have to have at least one clause, and each clause has to have at least one of these sub-expressions. All right. So what does that mean? So what this means is that we have a chance of running each of the individual clauses independently. If we look in terms of run star, and I changed the program slightly to have a 5 and a 6, run star says give me all the answers you can possibly produce. If we're thinking of this in terms of an if in a standard programming language, when you have an if, normally you have some tests and then you try one branch of the if based on if the test returned true or false. Here we're going to try every possible branch. So that's how we can get the multiple answers. So what's going to happen is when the conD has two different branches. If we just had equal equal Q5 as our whole program, we would get back 5 as the result. If we just had equal equal Q6 as our program, we would get back 6 as a result. In this case, we're actually able to try both of them. And if we do run star, we'll see we get 5, 6 back. Philosophically, we should not be concerned about the order in which the answers come back. We could have gotten back 6, 5 instead of 5, 6, and that would have been fine. So that's basically an implementation detail in terms of which order the numbers come back in this case. So we shouldn't really worry about that. Doesn't matter. So run star means it tells miniKanren, give us all the answers you have. We can also do a run one. Run one says give us the first answer that you find. And in this case, once again, because we're not supposed to be concerned about the ordering, we could get back either 5 or 6. In this case, we get back 5. It doesn't really matter. Could have gotten back 6 just as well. And of course, we could also do run 2 to give us back 2 answers if they exist. And we could ask for 3 answers if we want. It turns out there are only 2 answers in this case. Okay, so we could do a run 1000, and we'll get the same thing as if we had done a run 2, or run 10,000 or whatever. Okay? There are only 2 answers. And if you want all the answers, you don't have to put in a number, just put a run star. All right. This conD thing is actually very interesting for a number of reasons. First of all, we can add as many clauses as we want. So this is where it's syntactically similar to schemes cond. Okay, so if we want to have more than 2, that's fine. When you're thinking about the way conD works, first of all, I already said you shouldn't be concerned about the order in which the answers come back. You shouldn't be concerned about the order in which the conD clauses are tried or run by miniKanren. You really shouldn't be thinking at that level when you're writing your programs. Just trust that miniKanren will sort of do the right thing, whatever that is, and different versions of miniKanren could return the answers in different orders. That's perfectly allowable. One thing that's interesting about the way conD works is that each of the clauses really are independent. And what I mean by that is that this run star really is the same, this run star of the conD with 3 clauses. I could write something very similar to this using schemes list. What I could basically do is take a version of this program that was much simpler and just had the single call to equal equal. Okay, so I don't have a conD anymore. I just am saying that Q and 5 have to be the same. If I run this program, stick it inside of a list, I get back 5. And I could do the same thing here with 6 and 7. And now, instead of the list 5, 6, 7, I get a list containing the list 5, the list 6, and the list 7. And if I really wanted to, I could do apply append or whatever and flatten that list out. The point here is that these 3 calls to run star are independent of each other. They don't know anything about each other, right? So these 3 run stars each sort of exist in their own world, and they're not able to communicate with each other. In one world, Q is 5, in one world, Q is 6, in one world, Q is 7. And they don't know about the existence of any of the other values of Q. That's really what's happening when we have the conD. If you look at the first conD clause, we're saying that Q is 5. The second clause, Q is 6. Third clause, Q is 7. Those clauses do not interact with each other. Okay, so if I had more of my program here, if I called some function foo and passed in q or something like that, and here I have a bar in q, or here I have a baz in q, let's say. If I have three different q's, or three different functions I'm passing q to, the rest of these programs, the foo, bar, and baz, they don't know anything about each other. They don't know that they exist. They really are existing in separate worlds. And in fact, there is a interpretation of quantum mechanics, the many worlds interpretation of quantum mechanics, which behaves very similarly to this. The idea is that every time there's some event in our world, like some nucleus decays and sends off subatomic particles, something like that, then the universe splits. And the universe is always splitting. It's constantly splitting into other universes. And when we do some sort of measurement, when you have a quantum system that's in what's called a quantum superposition, could be in one of two states, let's say, and we measure that quantum system, we might measure a 1 or a 0 or an up or a down or something like that. One interpretation of this measurement phenomenon is actually we're splitting the universe when we do one of these observations, and that in one universe the value we measure is up, the other universe the value is down, and those universes can't communicate with each other. So as soon as we make the observation, the universe is split and they never know about each other. That's similar to what happens with the Kandi. We basically have three different universes, one where Q is 5, one is Q is 6, and one where Q is 7. They don't know about each other. They'll never interact with each other in any way. The only thing we can do, because we have this run star thing, is we can see the final answers at the very end. But that is something that happens when you see the final answers at the scheme level, not something that's happening inside miniKanren. When you're writing a miniKanren program, you're not supposed to know about what's happening in other Kandi clauses. Okay, and it can take some time to get used to that phenomenon, and sometimes it's not. Sometimes it gets in your way because you really want to know what's happening in these other clauses, but if you're in a pure version of logic programming, at least you're actually not allowed to know what's happening in the other branches. Okay, so each Kandi clause really is independent of the others. You can also think about this in terms of operating systems. For example, if you're familiar with operating systems and threads and processes and things like that, the way you can think about it is within the Kandi, we're actually starting three different processes. In one process, Q has the value 5, and another process, Q has the value 6, another process, Q has the value 7, and those processes are running independently of each other. They're not allowed to communicate. They have their own local memory, and not allowed to know. In fact, as far as they know, they're the only processes running. They can't even tell that there are two other processes running. And in some ways, that's a fairly accurate representation of what happens in miniKanren, because a lot of what is going on behind the scenes in miniKanren is actually scheduling when things happen. So you can think of miniKanren's implementation as, to some extent, as an operating system scheduler, scheduling these different processes that are being split off whenever you do a Kandi, for example. It's not too far from the truth. Okay, so Igor asks, has there been any work on parallelism in miniKanren? And the answer to that is yes, at a couple levels. One level is parallelism at the Kandi level, because basically Kand represents a logical OR. We're saying an answer exists, when we're doing a run 1, let's say, we're going to get an answer back if any of those Kandi clauses produce an answer. And you can, because these really are independent, you can make your program, make the miniKanren program parallel by forking off 3 different processes, for example, 1 for each Kandi. And that's easy to do, actually. That's really easy to do. That's about the simplest version of parallel programming you can possibly imagine. I've implemented it, other people have implemented it. The tricky part is that normally when you're talking about parallelism, and I'm going to make a distinction between parallelism and concurrency, normally when you're talking about parallelism, you care about performance. You're trying to parallelize the code so it runs faster. You can already see with this cond example that we might have trouble making the code run faster when we parallelize it. Why is that? Well, the reason it might not run faster when we parallelize it is that in this case, even though we have 3 different branches that can be executed independently, we don't have much work going on. Each one of these clauses is just a single call to equal equal, which is just a single unification. So that's a little more complicated than a call to equal, question mark, and scheme, but not that much more complicated. So it does some work, but not a tremendous amount. So the problem is that because when you write a real program in miniKanren that tends to have recursion in it, because of the recursion, you have many, many conds that you're encountering. Each cond you could split off, right? Some of the cond clauses are probably going to do very little amount of work, something like unifying a variable with 5, something like that. And those clauses, because they take so little time to execute, any sort of overhead that you get from parallelizing your program is going to swamp any gains in performance you get from the parallelization itself. So, if it takes a few microseconds or a few milliseconds to spawn off a new lightweight process or something like that, that might not be worth it. So the trick in parallelizing something like miniKanren, I think, is making sure that the different processes you're spawning off have enough work to do that it's worth the overhead. And you could do that a couple of different ways. If you're familiar with like work stealing algorithms and queues and things like that, you could try doing it that way. And we've tried implementing it that way, but we haven't gotten it to run any faster. Another approach you can take, and I think this is probably the most promising approach I know of, is something called granularity analysis or granularity annotations, where the programmer either puts some annotations on the program, or miniKanren has to do some extra work to try to figure out how much work is left to be done, and will parallelize the program based on the amount of work. So, if one cond clause is only doing a single unification, but 2 other cond clauses are doing lots of work, well, it probably is best to do the one cond clause, in a single thread or single process, and not bother splitting that off. But then when you get into the 2 other clauses, maybe you want to split off a new thread or process to handle one of those other clauses that's more expensive. So trying to figure out how much work is involved in the different conds is really important. And there's a version of Prolog called Chow Prolog that has some very neat annotations and inference for granularity analysis. So granularity analysis in Chow Prolog, for example, is one area to look at. But yeah, so it is very easy to parallelize cond. The problem is that it's embarrassingly parallel, but the amount of work you have to do in each clause can differ greatly. Okay, so logic programs tend to be extremely parallel, at least in terms of the ORs. There's also and parallelism, and also there may be parallelism at the level of the equal call. But trying to exploit all the parallelism in a smart way to make your program run faster is actually quite tricky. And another approach to this, by the way, another approach to parallelization is sort of a higher level approach, where you say, okay, I'm writing a big program, and some ways that big program encodes some big search tree. The search tree might even be infinite, but I know that at the top level, there are 4 different branches, let's say, that are going to be tried. So you could either by hand or in an automated fashion kind of break up the first level of the search tree and send off the 4 different subtrees of that search tree to 4 different processors. And if you do that right, you might be able to get the balancing a little better. Or maybe you go down to 16 levels if you have 16 nodes on a cluster or something like that. So that's another way to try to parallelize things. And something like Erlang might be really nice to do to handle sort of the command and control aspects of spawning those sub-processes off in a nice way. So that would be a really cool tool to be able to, maybe have the user say, I want to parallelize, the search tree down to depth 4 or something like that, and spawn it off to all these different processes I have. So a tool like that actually would be quite nice. Okay, so Daniel asks, has there been work on creating a profiler to automatically detect hot, Condy, or Lambda clauses? So I think this gets into, I think the intent of the question, if I understand it, is something like, is there anything like a JIT or a hotspot compiler or just-in-time compiler that's going to look at code that's run a lot and maybe make granularity decisions based on that sort of information? I think that would actually be really cool. I haven't seen any work, at least in miniKanren, on this. There may have been work in the Prolog community. I would be surprised if there hadn't. But I don't know off the top of my head of anything like JITting or dynamic profiling or anything like that for this sort of code. I think that would actually be really cool and potentially could be extremely useful. So if you have a recursive function or relation or whatever, you probably can tell just from just dynamically at runtime can tell, hey, well, this one just has a couple unifications and this other one has recursive calls and all that, right? Some static analysis. So I think you actually could do a lot in terms of determining granularity from doing something at runtime or doing a static analysis. The way it works in child Prolog, my understanding is that that the user writes annotations at the level of functions or relations. So if we were to define something called foo, if I were to define the foo relation or something like that, then I would put some annotation here that might say something like, foo takes x and y and it does something, and we're going to say something like the running time is big O of n squared, times, x squared times m, or something like, or x squared times y. So we could say something about the asymptotic running time of the algorithm. And in child Prolog, there's some sort of model of the hardware and some model of what it means to have this sort of asymptotic behavior. And based on that information that the programmer is putting in, child Prolog will try to break up the program in such a way that it's not going to run slower. It may not run faster, but at least it won't run slower. Sometimes it'll run faster. But I haven't actually played around with the child Prolog approach. It seems pretty cool, but I don't know all of the details. That would be something to look at. And the nice thing about that is once the programmer puts annotations on the code, the rest of it happens automatically, is my understanding. Yeah, child Prolog has lots of cool stuff in it, by the way. It's a Prolog, but what it really is it has Prolog syntax as sort of advanced experimental logic programming features, and has lots of parallelism features and/or parallelism and stuff like that. So definitely check out child Prolog. Has a lot of very interesting ideas that probably could be adapted to be used by other programming languages and even other paradigms. Because functional programming has a similar sort of notion of tons of parallelism, but it can be hard to exploit it, partly because the granularity figuring out the granularity can be really tricky. Okay. So yeah, so there's lots of opportunities, at least in theory, for parallelizing Kandi, because Kandi really is an OR. All of the clauses are tried independently; they can't interact with each other. It turns out that the way miniKanren implements Kandi is particularly nice. miniKanren's implement in general is very nice for parallelization in that there's a purely functional implementation. miniKanren's implementation is purely functional. With one possible exception, it has to do with the variable names, but we know how to make that purely functional, and sometimes we do. But we have purely functional implementations of miniKanren where there are no effects. And for those implementations, the Kandi clauses really are completely independent, not just at the level of the semantics, but also at the level of the implementation. So there's lots of sharing going on behind the scenes and things like that, but you don't have to worry about, you really could just send the Kandi clauses off to different processors without really doing any other work. In traditional Prolog implementations, the way they implement backtracking search has effects in it. They have these things called this thing called the trail that basically is keeping track of how you side effect variables, and when you want to backtrack, you have to undo these side effects. So the side effecting gives some very fast variable lookup, but it has this unfortunate aspect that you have to undo work. So so the basic model has some sequentialism kind of baked in at some level, whereas miniKanren, our model really is easily parallelizable without any changing. Here's a comment. From Igor or Vanilla. Mercury might be interesting to look into also. I think they've worked very hard on the compiler. Yeah, so Mercury is sort of a Haskell inspired logic programming system designed for doing programming in a large. And that has all sorts of very cool features in it. I don't know about their parallelism support. But the Mercury model in general is extremely interesting, and we should definitely talk about that one of these days. Kind of go into depth about the Mercury model and how we could try doing some of the things that Mercury does in miniKanren, because I think miniKanren actually would benefit from playing around with at least some of the Mercury approaches. It could potentially make some of the code in miniKanren run really fast. Yeah, so Mercury is a really cool language. Chow Prolog is a really cool language. There are lots of really cool languages related to logic programming, pure logic programming, impure logic programming, and hopefully we can look at some of those in the future. Okay, so that's Kandi, sort of in a nutshell. That the main point is that the clauses are used independently of each other. And as long as you're willing to just accept that fact and think about your programs that way, in a sense, there's really not much more to say about Kandi. It tends to give people trouble, I think, when they try to understand, when they try to think about exactly what's happening in the computer and what the underlying implementation looks like. And we will look at the underlying implementation of miniKanren, but and simplified versions like microKanren. But at least at a user level, it's actually really simple. Like, you basically have 3 independent miniKanren programs at this that are just running separately. You can think of it that way. They really are. Each clause really is like a separate little miniKanren program. Another thing I should say about Kandi, I guess, is that so historically miniKanren came out of this book called The Reason Schemer. So we were trying to teach logic programming to people with a scheme background. So the syntax of miniKanren reflects some schemisms, and Kandi is one of those. It looks kind of like Kand. As Ambrose points out in chat, it's a confusing name if you know a scheme, but that's where it came from. There's this unfortunate side effect to the naming, and in that we actually are conflating two different notions in Kandi. So two different notions we're conflating. So like I said before, you can actually have, you can actually have more than one goal inside of a Kandi clause. You can write things like this. Okay, so what does that mean? It means that within this clause, we're saying that Q has to be 5, or unify with 5, and then Q has to be 5 again. Okay, so that's duplicate. Doesn't really mean anything, special. We could reverse the Q into 5 if we want. Okay, so one of those turns out that you could delete either of these and then have the same meaning because the information is redundant. But the point is, syntactically, we're allowed to put in more than one goal within a single clause. All right. The tricky part here, to the extent it's tricky, it's not super tricky, but it sort of confuses two different issues. We have clause 1, we have clause 2, and we have clause 3. From a logic standpoint, this Kandi really represents an or, metaphorically. So we're saying, 1 or 2 or 3, if any of those produces an answer, any of those clauses produces an answer, then we have an answer for the entire run. Okay, so you can think of the Kandi clauses as an or. But within the Kandi clause, we have two different goals. Okay? And the goals within the Kandi clause are acting like an and. So for clause 1, we're saying that, either Q is 5, or sorry, we're saying Q is 5 and 5, 5 is Q. So we have an and there. So on the outer level of the Kandi, we have an or. Inside the Kandi, we have an and. So with, if we really wanted to break miniKanren down in terms of the simplest operators we can imagine, we would have separate ands and ors. If you want to keep the ands and ors separate, well, you just use Kandis with single goals in each clause, and then Kandi really is just acting like an or. But once again, this is sort of a syntactic thing we get from Scheme. Once you're used to miniKanren programming, I think the syntax is actually relatively nice. But if you're totally new to logic programming or logic, then you might get a little confused by the fact that we have two notions going on in Kandi. We have an or at the outer level, and within each clause we have an and going on. So that's something to be aware of. There's a simplified version of miniKanren called microKanren that actually does distinguish. It basically breaks the Kandi apart into two different operators: conjunction and a disjunction, or and and an or. They're separate. So just be aware that Kandi actually has sort of or behavior on the outside, but then within each clause has and behavior. Okay. All right. So that's about all I have to say about Kandi. Okay, so we've seen now 2/3 of the core miniKanren language. And we can see 2/3 of the language already just in this example. We have equal, which is our equality constraint. That's kind of the heart of logic programming. We have Kandi, which allows us to express or disjunction, or having multiple possibilities, any of which might give us produce answers, and we combine all those answers within the run or run star. And run is our interface between miniKanren and Scheme. Okay, so our logical operators so far are equal, equality, and Kandi, which allows us to express multiple possible worlds, if you want to think of it that way, or multiple possibilities. Okay, and like I said before, you can think of each Kandi clause as a separate process that's totally independent of anything else. Okay. Okay. So then just one more example here with the Kandi. Here I duplicated the first goal within this clause, and it happens to be redundant, right? So I'm saying that Q has to be 5. Q and 5 has to be equal. And then here I'm saying 5 and Q has to be equal. Well, obviously, if one succeeds, the other is going to succeed. But I could also change this, and I could change this to be a 4. So now I'm saying Q and 5 have to be the same, and Q and 4 have to be the same. And obviously, there's no assignment of Q that's going to make those both happen. So this first clause is actually going to fail. However, the second clause will succeed, making Q equal to 6. And then the last clause is going to succeed, making Q equal to 7. Okay. So we expect to see answers 6 and 7 back in some order. And sure enough, that's what we see. We could have gotten 7, 6 back. That would have been fine also. Okay. Doesn't matter. An important property. Let's talk a little minute about for a minute about the properties of some of these operators that we've seen. So one property that we already saw up here has to do with equal equal. I can reverse the order of the arguments to equal equal, and it doesn't matter. So equal equal is commutative. Okay, it doesn't matter. I can swap these back and forth. Means the same thing either way. I can also play similar games with the Candide clauses in terms of reordering those. So if I go back to my Candide clause, let me get rid of my comments. Okay, so once again, the first clause fails, the other two succeed. We're going to get 6 and 7 back. I can reorder these clauses any way I want. So I can move that failing clause to the bottom. I can reorder the 6 and the 7. Okay. Now I get back a different list. I get back 7, 6 instead of 6, 7. But what we should really think about these lists is a set of answers, not a list of answers. So 6, 7, and 7, 6, they represent the same set of answers. They're the same. Okay. So from that standpoint, I can reorder the Candide clauses any way I want, and I get back the same set of answers with a caveat, an important caveat. The important caveat is that this only holds, this only holds if I ask for all the answers that exist. If I do a run 1, for example, then I'm just going to get back whichever answer succeeds first, right? You know, whichever clause succeeds first will produce an answer. In this case, okay, it's 6. If I reorder the goals, in this case, I get back 7 first instead of 6. But that, you know, so it looks like I'm getting different sets of answers back, but that's just because I haven't seen all of them. That's why this property that I'm talking about only holds if you use run star, if you're trying to ask for all the answers. Okay. Okay. So those are two important properties. I can reorder the Candide clauses any way I want, and I get the same program. Has the same semantics. This, by the way, is not the case in Prolog. In Prolog, you have to be very careful. In standard Prolog, there are variants of Prolog that have different search mechanisms, but in standard Prolog, if you reorder the equivalent of the Candide clauses, you won't necessarily get the same behavior. In some cases, your program might actually go into an infinite loop, where with other orderings it might not. miniKanren uses a different search strategy than Prolog to avoid this issue, although we have different trade-offs. I mean, everything's a trade-off. So the trade-off is that the search we use will prevent us from going into infinite loops when answers exist, but uses more memory. So that's a trade-off that we make. But the nice property we get is that we can reorder these clauses any way we want, and as long as we do a run star, it's not going to affect divergence. Okay, so a question from Orchidacia. Okay, I can't pronounce that, but in Prolog you can type semicolon to get more answers one at a time. Can we do something like that in miniKanren? That's a very good question. So in this example we just saw with the run star, we got back 2 answers at once, right? We could have asked for 1 answer with the run 1. That would give us back 1 answer if it exists. We could ask for run 2. That gives us 2 answers. We could try run 3. And for run 3, in this case, we'll see that there are no more answers, right? But notice that if I want to get the answers back 1 at a time, I have to increment this number, right? Or I have to do a run star to ask for all of them. So if I ask for the first answer back with the run 1, and now I actually want the second answer, I do a run 2, I have to redo all the work to get the first answer in order to start working on to get the second answer. And if it takes, 10 hours to get the first answer, and the second answer only takes another 10 seconds, then that's wasteful, right? I'm redoing a lot of computation to get that second answer. The run interface in miniKanren doesn't support something like Prolog where you can type in the semicolon to just get the next answer. Underneath the hood, miniKanren actually does support exactly that behavior, because what's really doing is it's producing a potentially infinite stream of answers lazily. It's just giving the answers you asked for. Run is somewhat eager, and it's going to ask, you put a number, run 5, run's going to force all 5 answers, but then it's going to discard the rest of that potentially infinite stream. You can actually get your hands on the stream itself if you look at how run is implemented, and that's one of the things we'll do, is try to understand the run interface and how that's implemented. You can get your hands on the stream itself and do something like Prolog where you would get back 5 answers, but then you would get back, say, a procedure that would allow you to get back as many additional answers as you want without doing any recomputation. And we've gone back and forth about whether or not we want that to be part of the standard interface. In theory, I think it's sort of the case of the cobbler's children having no shoes, because it's so easy to do that, to get the stream and to process just as much as you want and keep the rest of the stream around. It's so easy to do it that in practice we don't actually do it. We know we can do it. If we wanted to, we could do it, but in practice we just have tended to stick with the run interface. And in fact, it would be quite nice to play around with alternate interfaces to miniKanren. But you can definitely do this. It's not built into the run interface. There are lots of other interfaces you can use to get answers back from miniKanren. One thing that you've seen already is that, by reordering these clauses, we can get answers back different ways, or in different orders, like 7.6 and 6.7. Well, one thing you might really want to do is if you're, say, running in Racket that actually has sets, maybe you want an actual set to come back. Maybe that makes it easier for testing. Because right now, if you just do equality on these lists in Scheme when you're testing, if you change your program slightly and get the answers back in a different order, then all your test cases might break unless you're very careful about that. That gets trickier when you only ask, for example, like a run 1, right? Now if I reorder the clauses, the run 1s look totally different. Like even having sets of answers won't help. Then you might want to have a special interface that, a testing interface that will keep running the program to see if you'll ever find the expected answer in the new stream you're generating, stuff like that. So there are lots of different run interfaces or testing interfaces you might imagine. They all have their uses. It'd be really nice to put together a package, a standard package of interface operators for miniKanren that let people experiment or play around with or use the particular operator they wanted. So have something like a Prolog style interface, have something like a test interface, have something like a true set-based interface, stuff like that. So that would actually be really fun, and that would actually be a good hacking exercise for us, because I don't think it'd be very difficult to do. Okay, so let's see. Doesn't the closure, okay, Daniel asks, doesn't the closure core logic run star return a lazy sequence? I thought in core logic it worked the same way as in the Scheme miniKanren. I mean, everything's lazy under the hood, but I thought that in core logic the run star, well, I don't know, that's a good question. So, okay, so something we haven't seen yet is that you can get back infinitely many answers from certain programs in miniKanren. We'll write one today that has infinitely many answers. And one of the problems with run star is that you'll get back all the infinitely many answers. Closure supports lazy data structures, has very good support for lazy data structures, So apparently in Clojure, when you do a run star, it's just going to give you back a lazy sequence, and then you can sort of prod that sequence for as many answers as necessary. So that's a good point. That's cool. In Scheme, if you do a run star, it's going to try to give you all the answers back, and it'll never come back. It'll just go in an infinite loop if there are infinitely many. So that's not so great. Okay. So apparently Clojure just gives you back a lazy sequence. That's really cool. All right. So you can see, I mean, we haven't even gotten to the third operator of miniKanren. You've already basically seen it for the most part. As soon as we start having two goals that are in a conjunction representing an and, that's essentially the behavior of the third operator in miniKanren, and that's called fresh. So let's talk about fresh real quick. But you can see we're already starting to get into very deep issues about parallelization, all sorts of user interface issues, issues of divergence when you have infinitely many issues. So even though we have a very small core language here, we haven't gotten into any of the extended constraints. We already have a lot to think about in terms of implementation and things in terms of user interface design, in terms of testing, all those sorts of things, right? So this, even though it's a very small language, it's actually very rich in terms of ideas. Okay, so let's look at fresh. Okay, so let me just start off and get rid of the kandi. Sometimes you want to introduce additional variables or logic variables in your program, like x and y. And that's the job of fresh. Fresh will let you introduce extra variables. So for example, I could unify Q with the list containing x, 5, y. So Q is my query variable, and I will get back a list with one answer. And that answer is itself a list. That's the list we constructed with the call to list. And that list has three different things in it. The first thing is the printed out, or sorry, displayed or reified. This is the reified answers. So the reified value of the variable x, the reified value of 5, and the reified value of y. Well, 5 is just a standard constant. If you type 5 at the terminal or the command line for Scheme, it's called the REPL, read eval print loop. This is the REPL, if you haven't heard that term, read eval print loop. So if you type 5, you'll get back 5. Okay, so 5 is how Scheme displays 5, or at least Vicari Scheme displays 5. And we can see that when miniKanren wants to display an answer containing 5, it just gives us back 5, just like Scheme would. Of course, if miniKanren wants to display an answer containing a logic variable, miniKanren is either going to display a value associated with the logic variable, or if the variable hasn't been associated with a value yet, it's just going to leave it as fresh. So this underscore dot convention. And because x and y are different logic variables that could potentially have different values, we see that underscore 0 and underscore 1, that the 0 and the 1 are different. That's saying that x and y could have different values. Okay? And this use of fresh allows us to introduce new logic variables whenever we want. And x and y, the scope of x and y, we can only refer to x and y within the body of the fresh. Okay, so in this case, just within this equal call. All right. Oh, thanks, Ambrose. That should be read eval print loop typo. All right. So fresh lets us introduce fresh variables. That's why it's called fresh. Now we can also introduce fresh variables up top, right? In the run itself, I could get rid of the fresh and do it this way. I have to change it a little bit now, because now I don't have a query variable. So that's actually a little, okay. I could do it this way. All right, so these two programs both have Q, X, and Y introduced as fresh variables, but the value I get back is actually going to be different. Now I get back a single answer still, but that answer itself contains 3 parts, one of which is the list we saw before. The other 2 parts are the values of X and Y on their own. And the reason is, if you use this extended run syntax where you're allowed to put in multiple query variables, what you're going to end up seeing at the end of the program is a value associated with each of the query variables in a list. Okay, so the value associated with Q, we know from up here, is going to be that list, _0, 5, _1, and then D, that's what we see. But we also, in this case, are going to see the values of X and Y, _0 and _Y. Well, we may not actually care about the values of X and Y directly. What we might really care about is what Q is associated with at the end of the program. So that's why we want to make sure that we have a separate fresh form we can introduce variables whenever. And we might want to make sure that the scope of X and Y are local. That we might be able, we might want to have more than one fresh XY in our program. And we want these X and Y's to be different from each other. Just like in Scheme, you can have let. You can say let X be 5, and then within a different let binding, you can say let X be 6, or whatever. Those are different X's. Okay, so that's the job of fresh, is to introduce new fresh logic variables, no association. Fresh also has another purpose, and this is similar to cond that conflates disjunction and conjunction, or and and. Fresh conflates the introduction of fresh variables in this list with conjunction, or sequencing, or and. So we're allowed to have more than one goal within the body of a fresh, and those are going to all happen. They all have to succeed in order for the fresh to produce a value. So for example, we might want to say that Y has the value 7. Okay, so the query variable Q is going to be list x5y, and the value of Y is going to be 7. In that case, Y won't be a fresh logic variable when it's reified at the end. Instead, it's going to be the value associated with Y, which is 7, and we'll get a slightly different answer from before. But the important idea here is that we can actually have more than one goal within the body of the fresh, and they all have to succeed in order for fresh to produce a value. So this is like an and, this is like a conjunction. Okay. So we're introducing fresh variables, but we also have the conjunction. So fresh, like cond, has 2 jobs. And you could actually break this apart. You could say we want separate operators to introduce fresh variables and separate operators to perform conjunction. And once again, that's what microKanren does. It's trying to distinguish these ideas and come up with very simple, sort of like the simplest definitions and implementations of these notions. But once again, in cond, we're trying to mirror the syntax of Scheme to some extent. So fresh looks a little like a begin or a little like a let. And it turns out that in practice, when you actually are using the language in and day out, sort of conflating the introduction of fresh variables and conjunction is actually kind of helpful. Okay, so another thing that I should show you is, here we have this fresh xy. I can also have a fresh that doesn't have any, doesn't introduce any variables, right? So I could just say let Q be 4, 5, 6, for example, and that works just fine. Whoops! Now here I forgot to give Y a meaning, so that's not going to work. All right. So I could say let Q be the list 4, 5, 6. I could also put in kind of a useless unification if I want. I could unify 7 with 7, which of course will succeed. 7's always 7. So in this case, I have two different goals within the fresh. It's acting like a conjunction. But in this case, I don't really need the fresh because it turns out that run itself, the body of run, can have multiple clauses in it. Or multiple goals within it, I mean, not clauses, multiple goals. So I could write this just as well, and this will work the same. Okay, so run itself metaphorically has a fresh in it. You can think of this as equivalent to having run 1q, fresh nil, right? And then having these clauses underneath. So you're allowed to have more than one goal inside the body of a fresh, or a body of a run. Okay. The other thing is that sort of metaphorically, you can think of the q in the run, the query variable, as being introduced inside the body of the fresh. We could, maybe make up some special query variable equal, and then have the query variable q that we introduced in the main syntax, and then maybe do a special secret hidden unification of equal to q, and that actually works the same way. Okay, so you can think of run itself as having a fresh inside of it, or introducing a fresh that has the query variable that we specified, and also lets us do a conjunction or an and of all the goals in the body of the fresh. And in fact, many implementations of miniKanren, run itself expands into a fresh of the query variable. So that actually does literally turn into a fresh that has that introduces the query variable. Not every implementation, but many of them do. All right, Ambrose asks, so with four logical operators, conjunction and so forth, can we avoid conflating concepts between them? Well, yeah, okay, so what are our operators? Let's think about it. So the operators we have, or the concepts we have, so we have conjunction, that's and. Okay, we have, oh, I don't know how well that will work. We have conjunction or and. We have disjunction or. Okay. We have equality. That's like an equality constraint. So that's really the equal thing. And we also have the notion of introducing a fresh variable. Okay. So those are all at the heart of miniKanren in terms of sort of the semantics. And then the last thing we have is sort of the interface. Interface to scheme, and also, sort of collecting the answers, reifying the answers, and all that. And that's the job of run. Okay, so for the conjunction and disjunction, so we have for the conjunction we have fresh, this conjunction, that's the and. Disjunction is the condi. Fresh introduces new variables also. And let's see, so equality is handled by equal. The tricky thing here is that, so fresh is doing two things, conjunction and introduction of fresh variables. Run is actually doing conjunction also. And of course, the other thing that does conjunction is within a single condi clause, we have conjunction. Okay, so there are actually three ways to express conjunction in miniKanren. Either just in the body of a run, you can have multiple goals. Within the body of a fresh, you can have multiple goals. Or within a single condi clause, you can have multiple goals. And all of those have to succeed in order to get an answer back. So there are actually three ways to express conjunction. Introduces variables, and it also performs conjunction. Condi expresses disjunction, but can also express conjunction. So those are all, doing double duty. Run also does double duty, right? So run acts as an interface, it collects the answers, it reifies the answers, it introduces a fresh variable in the terms of the query variable, and it also can act as conjunction. So we have a couple of different operators that can do different work, and we could split those up. And in fact, that's one of the ideas behind the microKanren work that Jason Heeman and Dan Friedman have been working on, is to try to separate those ideas sort of logically, and also to make the implementations simpler. Once again, it's a trade-off, because you end up with a very low-level language where you have, in microKanren, you basically have binary conjunction, binary disjunction, you have a separate operator, introduce variables, and it ends up being sort of like the assembly language of miniKanren. It feels very, very low level. So conceptually, it's very nice, but it's not so easy to program in. It's very awkward. The program is long, so it's nice for implementation if you're trying to port miniKanren to another language. It's nice to try to understand what's going on with the implementation. I think it's not so nice to actually program in. You want something on top of it that's a higher level. Okay. Okay, and Ambrose says, you could argue that sequencing goals is how you write a conjunction in any operator. That's right. So that's the way I think about it. And it's sort of like, there's a parallel to scheme, if you're familiar with scheme. Scheme has this thing called begin to sequence scheme expressions. It turns out that lambda has an implicit begin in it, so you can have multiple expressions inside of a lambda. The first expressions are just executed for their side effects. And it turns out that since let is metaphorically defined in terms of lambda, let also has an implicit begin. So once again, you have multiple forms in scheme having sequencing in the same thing in miniKanren. So if you look at it in terms of scheme syntax and miniKanren emulating scheme syntax, I think all of this is logical. It all makes sense. But you do have to realize that because scheme itself conflates some of these ideas, so does miniKanren. Okay, so it's not the purest expression of separate ideas. It's more like we're giving you a convenient syntax to actually write these programs. All right, so there's a lot going on in IRC. Let me see if I can understand this. Oh, okay, so someone's having trouble running. Okay, all right. It looks like they're okay having their discussion. Okay, so that's basically miniKanren. So you have these three logical operators: equal, which is a quality constraint; fresh, which introduces fresh logic variables and also does sequencing or conjunction or and of goals; conD, which does disjunction, and within each clause of a conD it has conjunction. So you have an or of ands, basically. And then you have run, which isn't really a logical operator. It's the interface between miniKanren and its host language, which in this case is scheme, but you're going to have something like run in any language. In core logic, there's something like run also. So all the versions of miniKanren I know of have something like run, or something equivalent to run, in order to get the answers back. You actually don't really need run. I think microKanren doesn't have run because you can just get the stream yourself, and if you're used to dealing with streams, you can sort of tease out the answers one at a time. That's really low level, though. Okay. All right. Okay, so that's it. That's it. And turns out that with the additional, so it turns out that that's sort of the core of miniKanren. So this is core miniKanren. If you're creating a cheat sheet on core miniKanren, you would have these aspects of it. But turns out there are a couple other things in language that we inherit from the host language, in this case scheme. So from the host language, we're getting a few things. We're getting things like the values, right? So we have things like numbers and Boolean constants and lists, right? Those are all coming from scheme. So the values that we can actually unify through a call to equal, those are all things we're inheriting from scheme. If we're in another language that didn't have, scheme has symbols, for example. So if we were in a language that didn't have symbols, like C, if we were trying to embed miniKanren in a language that doesn't have symbols, then we're not going to have those values. So the values that we're allowed to unify to some extent are going to depend on the implementation language, or sorry, the host language, the underlying host language we're building miniKanren on top of. And if you were to do a standalone miniKanren, which you could do, if you were to write a miniKanren compiler for a standalone version of miniKanren, you would have to decide which values you wanted to support. And the values supported for equal and closure, for example, and core logic, are different than the ones supported in Scheme. So the ones we're supporting in this version of the Scheme version of miniKanren, actually we only support a few types of values, whereas core logic, you have an extensible version of equal. You can basically unify all sorts of objects and things like that, as long as you teach equal about the things you want to unify. So that's something we inherit from the host language, are the values. Something else we inherit from the host language, in this case Scheme, are things like define and lambda, right? So if we want to define a function, we're getting those from the host language. Also, things like recursion. So miniKanren embedded in Scheme is going to inherit Scheme's recursion and Scheme's handling of recursion. So Scheme implementations are required to support something called tail calls, or tail call, proper handling of tail calls, tail call optimization. There are a bunch of different terms for these. Technically, there's some slight differences between things like tail call optimization and what Scheme implementations might do. If you're a Scheme compiler writer, tail call optimization might mean something a little different from proper handling of tail calls. But in any case, Scheme has very good handling of recursion. If you are in a language like Clojure, you have to explicitly say when you have a tail call with the recur form, I believe. And that has to do with the fact that it's running on the Java virtual machine and some design decisions there to try to make sure Clojure and Java play nicely. This particular handling of recursion and tail calls that we have in this version of miniKanren is inherited from the host language, from Scheme in this case. Okay, so we're getting the recursion from Scheme, and because of this, because we have recursion inherited from our host language, and we have lambda and things like that, we actually have a Turing-complete language. We can express anything we could express in any other language. In fact, we can do things like encode Turing machines in miniKanren. We can encode lambda calculus in miniKanren with just the operators we have, and these things like define, lambda, recursion that we're getting from our host language. Okay, so we already have a Turing-complete language. If we were to, once again, if we were to define our own standalone miniKanren that wasn't embedded in a host language, and we want to have our own standalone compiler for miniKanren, we would have to decide how things like recursion would work, or if we're going to have support for recursion. If we didn't have recursion in miniKanren, it would be kind of weird. I'm not exactly sure how we would do that, but I guess you might be able to have a loop-based, sort of iterative version of miniKanren, I guess. So, if we wanted to use a language that didn't have something like lambda, that might also be kind of strange or awkward. miniKanren also benefits from Scheme's macros for the syntax. Things like the run syntax we have comes from macros. The run syntax from Clojure comes from macros. The run syntax from Racket comes from macros. So if you're embedding miniKanren in a language that doesn't have macros for the syntax, it might be a little more awkward. Okay, so that's another thing we're sort of piggybacking on top of. So this really, so even though we only have these 3 logical operators in miniKanren and 1 interface operator, we're also inheriting some things from the host language. Okay. All right, a couple more questions in chat. Where does the .o syntax conflict with Scheme? This is a question from Ambrose. Where does it conflict with Scheme? Something like equal. Okay, equal. I think what Ambrose is trying to get at. Get rid of that. Let's go back to something that's going to give us a .0. Let's say. So the simplest thing we could do is just, unification that doesn't involve the query variable. Okay, so now we get this underscore dot zero representing the fact that the query variable Q remains fresh, right? So I think what Ambrose is trying to get at is that by deciding to print out, or to display or reify Q as underscore zero, we're also giving something up. We're giving up the ability to use underscore zero in our programs, because otherwise we won't be able to tell the difference. Okay, so for example, if I wanted to do something like unify the query variable Q with quote underscore dot zero, okay, Q now is not actually fresh. Q actually has a value. The value it has happens to be underscore zero, and I can make it underscore one if I want, for example, and we could say, or underscore 999 or something. And now it's indistinguishable. The underscore zero part is indistinguishable from having Q remain fresh, at least just from the output. Now, of course, since Q has a value, now I can make the computation fail if I try unifying Q with 5, because that symbol underscore 0 and 5 will conflict, and now I get no answer. But if I were to just look at the output, I wouldn't be able to tell the difference. I would think that Q is remaining uninstantiated if I didn't know what the program was. And miniKanren's not enforcing this, or our interface isn't enforcing this. If you want to use underscore dot zero inside your program, we're not doing anything to stop you. Just beware that you could end up with misleading answers. Okay, so this is one case where miniKanren's not trying to protect you. There are other cases. So I'll just tell you that in most implementations of miniKanren and Scheme that I've worked on, we represent logic variables as scheme vectors. So if you start using vectors in your program, miniKanren's likely to get very confused. Okay, we did that just to try to use a minimal part of Scheme. We could have done things like use R6RS scheme records, that sort of thing, to make it classier. This is one advantage that something like CoreLogic has, is there's a lot of software engineering effort that's gone in to make sure that you're not accidentally going to run into some of these corner cases. The standard Scheme miniKanren, we're worried more about pedagogical purposes and also in terms of research and kind of hacking and extensibility, making it very easy. Not that CoreLogic's not extensible, because there's things like the extensible unifier, but I mean things like it's very easy to hack the implementation. The implementation is very short, that sort of thing. You don't have to know that much about miniKanren to get in there and start playing with it. So because of those trade-offs and design decisions, we do have some sharp corners that you can cut yourself on if you're not careful, and we're not trying to protect people from that. Okay, so that's a good question, Ambrose. Okay, so let's see some other questions. All right, Orchid says, my friend had an idea to make a statically typed version of miniKanren inside a typed host language. We need to finish it. There was, okay, so the first modern version, in my opinion, the first modern version of miniKanren was actually implemented in Haskell. It wasn't, I mean, to what extent it was a typed miniKanren, you could probably argue, but it was implemented in Haskell. So there is, it is possible to do that for sure. There's also things like Adam Foltzer's Molog language, M-O-L-O-G, which is maybe somewhat inspired by miniKanren, and that's in Haskell, and that's my understanding is that's fully statically typed. And there's been lots of work in the logic programming world on statically typed prologues and statically typed logic programming languages, and that's an area I don't know much about. So hopefully some of the folks here who know a lot about type systems would like to play around with it. There are lots of things that I think would be really nice to express with type systems and miniKanren that I don't know how to express. I will show you one thing real quick. Okay, so we've seen the core language. I'll show you just one other thing that I mentioned, and that's the symbolo thing. So we can write something like symbolo-q. Symbolo is a constraint that's built into the version of miniKanren I checked into the Hangouts repository. or the uncourse's repository. And if you say that Q is a symbol by using the symbolo constraint, if you look at the answer, we'll see that the answer looks a little strange. What this answer says is that, first of all, there's only one answer. We did a run star, but we got back a single list. There's one answer. The first part of this answer tells you what value is associated with Q. And that's _0. So Q is unassociated with anything. The rest of the answer shows you what constraints are on Q. And in this case, we have a symbol constraint or symbolo constraint saying that Q represents a symbol or symbolic value. So Scheme supports symbols. Another version we could do that might be more applicable to other languages would be numbero. Okay, so now we're saying that Q has to represent a number. And we can see that in the reified answer. There's a number constraint on Q. And if you violate this constraint, then miniKanren is not going to produce an answer. It's just going to fail. So if we say Q is a number, but then we unify Q with a symbol rather than a number, then we'll get failure. Okay. If we unify Q instead with a number, then it'll succeed, and the constraint will go away because there's no way to violate it then. So in this case, I just go back to list 5. There is no numbero constraint anymore because we've essentially discharged that constraint. You know, now we know the value of Q. We know it's a number, so there's no way to violate it. And these are very simple examples of type constraints or type-inspired constraints. These are very similar to number ? or a symbol ? in Scheme. But what I would really like is to have much more sophisticated type constraints where I can do things like say, okay, this variable represents an association list of symbols to numbers or something like that, which comes up a lot when you're writing interpreters or type inferencers or, actually almost any sort of sophisticated program is going to have more complicated data structures, and you want to enforce that a variable actually has a certain type as it gets instantiated. But because these variables don't actually have to have a value, you don't want to force the variable to have a value in order to check it. Okay, so you want to sort of lazily enforce this. And that's what symbolo and numbero do, but they don't have much structure. So having a general system where the user can specify a data type and miniKanren will then enforce the data type constraints and reify them in a way that are understandable when you haven't fully ground fully instantiated the variables is something that would be extremely useful. And I'm working with a couple of folks at Utah, like Michael Adams, for example, to try to understand how to do that. But it gets a little tricky in terms of interactions between the different constraints and things like that. I mean, there are different ways to implement it, but you're still going to have to solve all these constraints. And if I have constraints on 10 different data structures and they're interacting in arbitrary ways, making sure that they all compose nicely and you can tell when there is no answer and fail as soon as possible, and make sure you have the simplified representations of data structures and things like that. That takes a little more work than sort of what maybe what the most naive approach would be. So that's an example where some typing would really be helpful, either static typing or runtime constraints like the numbero and symbolo, but extended to deal with different data types. That would be extremely useful. All right. Yes, and also Igor points out that miniKanren.org, which is the miniKanren website, has links to several Haskell implementations, for example, if you're interested in typed versions of miniKanren. Okay, Vlad asks, is there any way to get symbolo and friends in cKanren in Racket? cKanren, which is developed by Claire Alvis, and that implementation originally started in Scheme, so Dan and Claire and I and another student at Indiana, we worked on that version of miniKanren called cKanren, Constraint Extensions of cKanren. And there's a paper about it on the miniKanren website. Claire went on to port that to Racket and then rewrote it. And I don't think the rewrite's quite complete right now. So cKanren's sort of in an intermediate state. cKanren does support Symbolo and Numbero, at least the modern cKanren does. So so that actually should work. I think the tricky part is finding sort of the right version of cKanren that handles everything properly. If you want to write, if you want to run this in Racket, the other thing you can do is just take the scheme code, run it in Racket under the R6RS compatibility mode, for example, and that should work. Or with tiny changes should work. So if anyone wants to work on that, make sure they get everything working, then we can put a Racket version in the uncourse repo. Okay. Yeah, require cKanren / miniKanren. Yeah, so you could try the cKanren that is currently associated with Racket and see if that works with everything you want. If not, we might have to check with Claire, and we can ask Claire to come on and kind of talk about the state of all that. That'd be cool. Yeah, so that version apparently, okay, so the version of cKanren you have apparently doesn't have Symbolo and Numbero. I don't know if you have to load anything else, if you have to do any other requires. I know that at least at one point Symbolo and Numbero were supported by cKanren, but keeping track of sort of the right stable version of cKanren is a little tricky right now. Hopefully that will all stabilize. Yeah, so if you run it under R6 mode, that might be the easiest thing right now until Claire finishes stabilizing that. Okay, so I think I'm going to stop right now with the screen sharing and all that. So we covered the rest of the core miniKanren. So far we've talked about equal, which is equality constraints. We've talked about Kandi, which allows you to have different clauses that operate independently. That's like an OR. We've talked about fresh, which can be used to introduce fresh logic variables and can act like an AND or conjunction. And we've talked about the interface operator run. And I also showed you a couple other constraints, Symbolo and Numbero, that I don't consider part of the core implementation, but they're definitely useful to have. Okay, and the reason schemer, the book that Dan and Oleg and I wrote, they just have the equivalent of Kandi, fresh, equal, and run as sort of the core part of miniKanren. The book actually has something called Kandi, which is interleaving Kandi, which is separate from Kandi, but basically the Kandi in the book, something very similar to that is like our Kandi. So the same ideas are in the book, it's just slightly different implementation. So anyway, that's the core language of miniKanren, and there are various ways you can extend that. You can extend it to be impure, to do things like cut in Prolog or something called committed choice, and do some other impure or extra logical operators that turn out to be useful. And they can be useful when you want to interact miniKanren with scheme, or miniKanren with closure, or miniKanren with whatever host language you have. And we'll talk about the impure parts also. But I want to start with the sort of the pure version. And there's a whole lot you can do just with the pure version. If you want to write more complicated, larger programs, the pure version is fairly restrictive in a lot of ways. You find you want other constraints, for example, or other operators to deal with. But it's enough already to have a Turing-complete language. You can do all sorts of very interesting computation. Intellectually, it's very interesting, and it also forms the foundation for the rest of miniKanren logic programming. So it's important to understand how all these operators work. And I think next time what we can do is probably look at something like append and see how that works, and then we'll have a recursive definition and go into some depth about how exactly it works and what happens when you reorder goals and so forth. It turns out that you get a lot of very sophisticated or very subtle behavior with append. And in particular, one query that would give you an infinite loop with one ordering of goals will fail in finite time with other ordering of goals. And it turns out that this is very close to, very much related to sort of the heart of logic programming. And we can also talk about maybe some ways to get around at least some of the disadvantages of those approaches and some other approaches that people are looking at to improve the conjunction, the and behavior of miniKanren, to make miniKanren somewhat less susceptible to reordering goals within a conjunction, within a fresh, within a run, within the clause of a condi, reordering goals within the conjunction turn out to not have some of the nice properties that we have when we reorder the disjunction with the condi clauses. So we'll look into that in some detail. Now that won't be this coming week because I'm going to be in Washington, D.C. at the end of ClojureConf and the Scheme Workshop, but I think the week after we can do another hangout and look at all the append stuff, which is a lot of fun. Okay, so that's all I have to show us right now. So we've already seen actually all of miniKanren, all of the core miniKanren. There are lots of constraints we could add, there are lots of operators that are extra logical we can add, but the stuff we've seen, that's basically the heart of the reason schemer, for example. It's sort of at the heart of my dissertation, and we can extend it in various ways to make the language more expressive, to make it more efficient, but we already have enough power to write Turing machines and lambda calculus interpreters and all sorts of fun things like that. Okay, so so the comment in the Hangout that it would be really cool to hear from Claire and learn about cKanren. I totally agree. I think maybe once we get sort of the foundations down, then we can start having some guests on who will talk about the things they're working on. So Claire and the work on cKanren would be really cool. Having David Nolan talk about the Clojure version, core logic, would be really cool. Having someone come on who does nominal logic research would be cool, and having Dan and Jason come in and talk about their research on microKanren, for example, would be cool. So yeah, I'd definitely like to get some folks on to talk about these things. Okay, so I think we should go ahead and, I went on a little bit longer than I wanted, but I wanted to get the rest of the language in. So now I'm just going to open it up and we can talk about whatever we want. If people have to go, that's cool. If people want to stay, that's cool. And we can talk about whatever. If people have questions, that's great. If people want to talk about particular problems that they're interested in solving in miniKanren, that's great. And if people want to do a little bit of hacking, that's great. Whatever. I'll open up the floor.
I have a question.
Sure.
It's more from the book, so I'm gonna share my screen so everybody can see it, because that's just one of the problems from the book, that even though I read it a few times, I still kind of like fuzzy on it.
Okay, this is the reason schemer.
Yeah, the reason schemer. Can you see it? Can you see it?
Yep. And by the way, someone was asking, do you recommend reason? Daniel's asking, do you recommend reading the reason schemer, or is your dissertation a better choice? The reason schemer is designed for sort of bright but ignorant high school students, and is designed to be a little book, if you're familiar with the other little books in that series.
Yes, I have read them.
Yeah, so they have a very particular style, Socratic dialogue approach, stuff like that. Some people like that style, some people don't. My dissertation, I tried to be as self-contained as possible, but it's okay, I'm getting feedback from someone's mic.
Oh, sorry. Yeah, sorry. That's mine.
Was it wrong? Anyway, my dissertation, I also tried to make self-contained. It's written in a different style, right? So it's an academic document, but I tried to make it very readable. And I think it just depends on what it is you want to look at, or what it is you want from a book. I think look at my dissertation. That's freely available online. It's on the miniKanren.org website. And if that doesn't have the right feeling, or if that looks too intimidating or whatever, maybe go to the little book. So I think it's partly a matter of preference and reading style and so forth. Okay, sorry. Your question about the book?
After reading the book a few times, this particular example on the screen, I know from where the first zero and the second one are coming, but the rest of it kind of like doesn't add up to me, and I wanted to see if you could actually go over it or something. 'Cause I know the first two values, but after the other ones, I just don't see it.
Sure, sure. Okay, so okay. Why don't I tell you what? Why don't you send me the chapter and frame number for the question for the thing you want to look at, and maybe we can look at that next time. I think
Okay.
to do it right is going to require some setup, and since we haven't, I mean, to do it in a way that everyone can follow, I think is going to
Okay.
require a little setup and showing how to write all the helpers and all that. So I'm happy to go over that. I think to set it up, probably need to prep a little bit more and walk
Yeah,
people
because you'll
through.
need Caro and Cooler, and I think you need
Sure,
Appendo.
sure. So that it probably takes like 15 or 20 minutes to really set that problem up. Okay, but yeah, that's something I'd be happy to
Yeah,
talk about.
I'll email it to you when we're done, so you'll have
Okay,
it.
okay, thanks. All right. Um, okay, that was a good question. Any other questions that people have, or any other topics that people want to know about?
Could you talk more about what you want to use say we have our statically typed dialect of miniKanren. You use the Symbolo example. So I assume you'd want to use the types to prevent certain unifications when you have a Symbolo, for example. But that gets really weird because unification is both a predicate and a assignment. So I assume you've thought of all these things and realized how insane. I guess the type system would be opt-in to some degree because of how flexible unification is. I don't know. I don't really have a question. I'm just talking.
Okay, so is your question how these types or these type predicates or type constraints or whatever are going to interact with unification? Is that basically what you're asking about?
So I'm assuming that we've got a static type system that somehow prevents bad unifications, which I assume your example there, I guess it made sense. No. So you propose that we could either check this at runtime or check it at compile time. So I guess I'm thinking about compile time because I don't know how you do it at runtime.
Sure. Well, I mean, we're already doing it at runtime in a simple way, right? We just have a few of these constraints.
Okay.
And I think you could do it at runtime with a more sophisticated set of constraints. It might be a little tricky to implement, but I think it's possible. Okay, I don't know about the static doing it statically. I think that's not as clear.
So the point of yeah, okay. So I guess I want to know how you'd use the type system. I guess maybe you don't know yourself. Like if you had this expressive type system, how would you use it to make your miniKanren programs stronger?
Yeah, so I guess part of the issue is that with those conds, each condi clause can produce an answer, right? And what you want to make sure is that if I give a specific input to a program, that each condi clause is running independently, and if I give a ground, if I give inputs to a miniKanren program that don't have any variables that are just an actual scheme value with no logic variables in it, I only want one of those condi clauses to succeed in most cases. So one of the reasons we have things like numbero and symbolo is if you're writing something like a interpreter for a scheme inside of miniKanren, then you want to have a special case for numbers. It's like, okay, I've recognized that you have a number here, or you might have a number here, so do numbery things. And in another case, like, hey, maybe I want to represent variables as symbols, for example. Hey, you've got a symbol here. Okay, let's treat this as a variable. So part of this is is things like doing the equivalent of matching, pattern matching, based on the types of objects. That's one use for these constraints. And another thing is just making sure that everything is sound. That if something, if you have a variable supposed to represent an association list, that it doesn't end up being 5 at the end of the run or something like that. So those, I think, are the two main uses we have, is just in order to dispatch on the value based on its type, and the other thing is to make sure that we don't end up with basically nonsensical answers. And it turns out that in Scheme, I feel mostly okay with having a runtime type system. That doesn't really bother me. I mean, if you read the posts of Bob Harper, he says that Scheme's actually statically typed. It just has a single type. But in any case, the Scheme type system, for most of my purposes, usually is fine. In miniKanren, I find it less fine because at least in Scheme you have ground answers, right? Like, if you have a list containing 5 coming back, you can probably figure out what the 5 means. If you have a list containing _0 and _1 and _2 coming back, you have to try to figure out, what does that _0 really mean? It means that some variable wasn't bound, but what is the domain of that variable? It's not as clear. So sometimes I'll write a miniKanren program, and if it's a complicated program, I'll do a run 50 and I'll get all these answers back, and then the answers will have underscore dots, numbers after it, and I'll spend a lot of time trying to figure out, well, does that answer actually make sense? And a lot of times I'm like, no, that answer doesn't really make sense. The answer has to be more restricted than this. So just interpreting the answers or trying to find errors in your program, it's very difficult when you can have these fresh logic variables representing unknown domains in the answers. It's quite tricky to understand what those mean. So that's where I would like either saying static or dynamic coming in. Adam Fulcher would be a good person to talk about this, because he's spent some time and he worked on that Molag system. Last time I talked to him, which wasn't that long ago, he thought that a runtime or dynamic constraint-based system would actually be the thing that would be most useful for miniKanren. He actually thought that the static type systems, at least the ones that he was thinking of, were too restrictive. And I'm not sure. We can get him on and he can explain more about what he thinks. The other thing that would be kind of cool, and this is, I think, a different use of types, would be something like looking at dependent types, something like Idris, implementing miniKanren in Idris, or somehow getting it involved. There's a lot of logic that you can see in type systems sometimes, right? And so allowing a type system to do logic programming, or getting miniKanren involved more in a system that dependent types would be really interesting. That's I think is somewhat separate problem, but that'd be another place where miniKanren and types could interact. Does that answer your question at all?
Yeah, I'll hit up Adam, because I was going to ask you how far you've got with Adam, but I might as well just ask him. Yeah.
Sure, and Adam actually gave a talk that was recorded at the ClojureConf West, I think 2 years ago. There was this miniKanren miniConfo.
Yeah.
And I forget if that video made it online. I hope it did. But
I have seen it.
Okay. So he gave a talk on that, and I'm not sure how much further his language got. It wasn't miniKanren by the time he finished it. It was sort of inspired by miniKanren. I think maybe it started out as a type of miniKanren, and then it kind of diverged when he started playing around with the ideas. But I don't think he's pushed it that much further. But I think he ran into some issues that made it kind of awkward. So he was thinking that static typing probably wasn't the thing for miniKanren, but I'm not, we could have him on and have a more nuanced discussion, because I'm not sure I understand exactly why he thinks that way. Would something like gradual typing or something equivalent to typed racket or typed closure, could anything like that make sense in sort of the world
like
of these
at
constraints?
some point you're going to have to interact between untyped miniKanren and typed miniKanren or something. So I don't know. gradual typing seems to seep in everywhere. If you, from Idris to Haskell, there's gradual typing. It's like,
Sure.
yeah, it would probably get insane at some point. Yeah, with logic programming.
Yeah, so I mean, and that's just an area of the design space that we just haven't explored. Partly because Dan and I are longtime schemers. Oleg obviously knows all this stuff about types, but because we're coming from the scheme background, and there are lots of other interesting problems to explore other than the types and logic or relational programming. But I actually think it's time that we should start exploring some other the typed approaches, because not being able to express a given association list, for example, is really annoying.
Yeah.
Yeah, and some of the uses of miniKanren tricks we play, partly because we don't have a type system. Sometimes we have to kind of stand on our head to do tricky things, whereas if we had a type system, those may be more straightforward. But I'm not sure, because I haven't had a type system to play around with. So, and any of you type gurus who want to play around with this, please, I encourage you to be my guest. So yeah, we should have Adam on and see if he can talk about the types issues. All right, cool. All right, well, it looks like we're 2 hours in. I think might go ahead and finish up, because I know I'm supposed to do some miniKanren hacking actually with people later today. But oh yeah, another person I want to get on is maybe Rob Zinkoff. We've been doing some probabilistic miniKanren stuff. That's really cool. So yeah, so lots of people to bring on to talk about stuff. But yeah, so thanks everyone for showing up, and yeah, I think 1 or 2 more of these, and we'll be ready to start hitting more advanced stuff, and then kind of open it up and start doing some projects and things like that. So thank you all, and like I said, not next week, but the week after, I think we'll be able to. Yeah, no hangout next week, because I'll be in Washington, D.C., and I don't know about my internet and all that, but the week after I should be good. Okay. All right. Okay, well, have a good week, everyone, and I will hope to see you all next time. Happy hacking.
Thank you.
Stuff to broadcast. Sure.